Hello everyone. In this video we will talk about random variable. So let's say we are running an experiment and we're collecting the output, and let's call this output X. Now this output will have different values. If we can assign a numerical number to this output X, like for example 1, 2, 7, 9.3 and so forth, then we can call this a random variable. Where is the randomness coming from? Because I cannot predict with certainty the outcome of the experiment or the data I'm collecting. Now, if the random variable X has discrete values like 1, 1.5, 2, 2.3, and so forth, then we call it a discrete random variable. If the random variable X can have infinite possibility of values, like 1.11112, 1.11123, and so forth, then we call it continuous random variable. We will start with the discrete random variable, and let's take this example. The number of flaws in a 1-inch length of copper wire manufactured by a certain process varies from wire to wire. Overall, 48% of the wires produced have no flaws. So now we can call the number of flaws as our random variable X. So there are 48% of no flaws. So X equals 0, no flaws, and there is 0.48. So now this is the probability of X. 39% have 1 flaws. So when X is 1, there is 0.39%. 12% have 2 flaws, so 2, there are 12%, so that is 0.12, and 1% have 3 flaws, so this is 3, 0.01. So now our random variable X has only this discrete value, and these are the corresponding probability for every value of X. So I can write probability X equals 0 equal 0.48. Now this here is the probability mass function. When you list all possible values of the random variable X and the corresponding probability, then we call it the probability mass function, or sometimes we call it the probability distribution, and it's abbreviated as PMF. If I plot the probability mass function as a histogram, then we call the probability histogram. So for this example, the possible values of X is 0, 1, 2, 3. So then X equals 0, there is a probability 0.48. So I draw a bar here with height 0.48. And when X equals 1, it's 0.39. So I draw here a bar that is 0.39. And when X equals 2, the probability is 0.12, so that could be something like this. And when X equals 3, the probability is 0.01, something like this. Now this we call it the probability histogram. And if I want to express probability X equal or less than 0, then that will be 0.48. Now if I say probability X equal or less than 1, that will be the probability X equals 0 plus probability X equal 1. And that will be 0.48 plus 0.39 equal 0.87. And we can do the probability of X equal or less than 2. Then I add this 0.87 to the probability X equal 2. And this will come 0.87 plus 0.12, so that is 0.99. And if I call probability of X equal or less than 3, that will be 0.99 plus probability X equal 3, and this will come to 1. Now these probabilities, we call it the cumulative distribution, and we can represent it by f of X, which means the probability X, when X is large here, capital, that's the symbol of the random variable. This lower case here, an actual value. It could be 3, 2, 1. So the cumulative distribution function, or the symbol CDF, is the probability x equal or less than little x. So if I plot these, that will be like this. So now here I'm plotting the cumulative distribution function. So when it is 0, the probability is 0.48. When it is equal 1 or less, it is 0.48 plus 0.39, it's 0.87, which is this. When the probability equal 2 or less, it is 0.99. And when the probability equal 3 or less, it is 1. And then this, we call it the CDF, or the cumulative distribution function of the random variable x. And we just discussed this, the cumulative distribution function, the sum of all probability for x to have every possible value or less, we call it the cumulative distribution function. If I add all possible probability, they should add up to 1. That means if I add all this probability here, they should add up to 1. And this is this one. Okay, this example we just did earlier. So the next topic is the mean of a random variable and the variance. So when we used to have a population and we list all possible outcomes, we find the mean of x by summing all these possible values divided by the total number of data in the population. So now when we think of random variable and probability, the mean of the random variable x equal the following. It's the value x1 time how often does it happen. So that is x1 time the probability of x1. For example, if the population here n equal 1,000 and x1 happened 100 times, then probability of x1 will be 100 divided by 1,000. So let's write it here, 100 divided by 1,000. That's this probability time 100, the value of this random variable, plus x2 time probability of x2. Same thing, if x2 is 150 and it appeared 20 times, then it will be 150 times the probability, which is 20 divided by 1,000, and so forth. And that's how we calculate the mean, which is this equation. And sometimes we call it the expected value of the random variable x, or mu. In this course, we always gonna call it mu, but in some publication they call it ex, expected value of x. Next, we will talk about the variance of the random variable. If we have a random variable x, and this random variable x has this possible value, then the variance will equal, and we will represent it as this sigma square x. It will be the difference between x1 and the mean squared times the probability of x1 plus x2 minus mu x squared times the probability of x2 plus x3 minus mu x squared times the probability of x cubed. And that's how we calculate the variance. Now, if you have more than x, you have n of them, then this is the general equation. Now, it is easier to calculate the variance using this equation. And we have proven that these two equations are the same. So here, to prove that, I can express it as the variance of x squared equal summation x, I'm gonna square these, x squared minus 2x mu x plus mu x squared times the probability of x. And I can express this as the summation of x squared times the probability of x minus the summation of 2x mu x times the probability of x plus the summation of mu x squared probability of x. And this is the summation of x squared probability of x, so it doesn't change, minus 2 and mu x are constant, I can take them out, plus mu x squared is a constant, so I can take it out, summation of probability of x equal. This is the summation of x squared probability of x minus 2 mu x. Now this is the mean of the random variable x. This is the definition, which is this one here. So I can write this as mu x plus mu x squared. Now this one here, the summation of all probability, and we know the summation of all probability will equal 1. This is this one. So this is equal 1. Now this is the summation of x squared px minus 2 mu x squared plus mu x squared. And finally, this is the summation of x squared probability of x minus mu x squared. And this is exactly this one here. When you code a system or you write a code, it's easier to calculate the variance using this equation. Also in quiz and test. All right, let's look at this example. A certain industrial process is brought down for recalibration whenever the quality of the items produced falls below specifications. Let x represent the number of times the process is recalibrated during a week, and assume that x has the following probability mass function. Find the mean and variance of x. Okay, the mean of x, mu x, will be the first possible value times its probability. So that will be 0 times 0.35. The second possible value, 1 times the probability, 0.25, plus 2 times 0.2, plus 3 times 0.15, plus 4 times 0.05. And when you calculate these values, you should get 1.3. So in 1 week, you will calibrate it 1.3 times. Now to calculate the variance, it is 0 squared times the probability plus x squared, x now is 1, times the probability, plus 2 squared times the probability, plus 3 squared times 0.15, plus 4 squared times 0.05, minus mu x squared, minus 1.3 squared. And when you calculate this, you should get 1.51. All right, the probability histogram, which is this one, you list all possible values for the random variable here, and the bar height represent the probability. And in the previous example, what I just showed, we plotted the histogram for this one. It will be something like this. The height of this one is 0.35, the height of this one 0.25, and the height of this one, the final one, is 0.05. And if I add all this probability, I should get 1. Okay, let's talk about the continuous random variable. So now the random variable x does not have discrete values, but it could be a continuous value. So now we're talking about the probability density function instead of the probability mass function. And a very popular probability density function is the normal distribution or the Gaussian density function, which looks something like this. So it describes many phenomena, where here these are x, these are the possible values for x, and this could be 70. So the majority of the data or the outcomes will have value around 70. And if this is 10, only few data point will have the value 10, and so forth. So that's what we mean by the probability density function. And usually this curve here is represented by f of x, which is the probability density function. And we will learn in chapter 4 different probability density function: exponential, normal, binomial, and so forth. Now, the same thing as the probability mass function If I add all possible probability for each outcome, I should get 1. So the summation in the discrete, the summation of probability of x add to 1. In the continuous case, it's the integration of the probability density function f of x dx equal 1. Here it will be the minimum possible value for x. Here will be the maximum possible value for x. If x can go from minus infinity to infinity, then this is the general formula. In the discrete case, random variable, you can have probability the random variable x equal 1 and you have a value. It could be 0.25. But if x is a continuous, then there is nothing such as probability x equal 1 and you will get a value. It's usually 0. It's like here, if I tell you what's the probability x equal 65, it's, as we will see, it's the area at that location. So it's like you are integrating from 0 to 0. That will give you 0. So when it's a continuous, you have to specify a range of value for the random variable x to calculate probability. And this is this one here. So what is the probability that the random variable x will equal or larger than a and equal or less than b? Then it's the integration from a to b of the probability density function f of x dx. So in this case, if a is here and b is here, then you are calculating the area under the curve from a to b. And that will give you the probability that the random variable x larger than a and smaller than b. And that's how we calculate probability for a continuous random variable. Now, what do you think the area under the whole curve? So if this is a probability density function f of x, so if I integrate this from minus infinity to infinity, I should get 1. So the area under the curve, if that is a probability density function, it should always come to 1. And if you want the probability of x equal or less than a, then it is the integration from minus infinity all the way to a. So that will be this region. If I want to find the probability of x larger than a, then it will be this area, x larger than a. Same thing with the discrete random variable. I can calculate the cumulative distribution function f of x, which is just the probability of x, the random variable x equal or less than x value here. So it's the integration from minus infinity to x. So if I am giving f of x, it will be the probability, for example, if this is f of x, then for x value here, let's say a, I calculate this area and that will be this value. And then I calculate for b this area and it will be this value. And then for c, this whole area and it will be this value. And for d, this is c, and d, and so for this one until infinity. When I calculate this area, it will be 1. So the curve will look something, it depends on the function, but definitely the maximum value it will have for the cumulative distribution function is 1. Now, if I want to calculate the mean of a continuous random variable, same thing, instead of summation, now integration. When you calculate the mean for a continuous random variable. For a discrete, this is a summation, xp of x. For a continuous random variable, a summation becomes integration because there are many possible values for x. And p of x, probability mass of function, now it will be f of x, probability density function. Same thing when you calculate the variance. You can use this equation, but it's easier to use this equation. So instead of a summation, it's an integration since it's continuous. instead of P of X probability mass function, it is probability density function. Same. You can see the analogy between discrete. We do it summation x squared P of X minus mu of X squared. That's for discrete. This is for continuous. Let's look at this example. A hole is drilled in sheet metal. So we have a sheet metals here, and we are drawing a hole here. And then a shaft is inserted through the hole. Let's see, this is the shaft clearance is equal to the difference between the radius of the hole and the radius of the shaft. So this is the radius of the hole, and this is the radius of the shaft. And this is the clearance. The shaft clearance is equal to the difference between the radius of the hole and the radius of the shaft. Let the random variable x denote the clearance in millimeter. The probability density function of x is this one, and we can plot it for different value of x, and this is f of x, the probability density function. So that is the PDF. Okay, now one component with clearance larger than 0.8 millimeter must be scrapped. What proportion of component are scrapped? Okay, if we look at this graph, here is for our application, here is the threshold. So the clearance must be less than 0.8. Anything larger than 0.8, we throw it away. So what proportion of component are scrapped? So they want to know what is this proportion. Are we throwing 30%, 50%, 70% of this metal with this hole, and so forth? So we need to find the probability of x equal or larger than 0.8, because that will give us this area, and that will be the proportion of sheet metal that we have to throw. Okay, so this is the probability from 0.8 to the maximum possible value for the random variable x, which is 1 here, of f of x, which is 1.25, 1 minus x4 dx. So I'm using this equation to find the probability. And if we do that, then this will be 1.25 x minus 1.25 x5 over 5 from 0.8 to 1. And that is 1.25, 1 minus 0.8 minus 1.25 over 5, 1 to the power of 5 minus 0.8 to the power of 5. And if you calculate this using your calculator, you should get 0.08192. So there are 8%, 0.1 of the components will be scrapped. Okay, find the cumulative distribution function f of x. To find f of x, it is the probability from the lowest possible value, in this case it is 0, to x, and x can be anything, and the integral of the probability density function f of x, which is 1.25, 1 minus x4 dx. This is the same integral here, except instead of 1, I'm going to have x. So I should get 1.25x minus 1.25 over 5 x5 from minimum value is 0 to any value of x. I should have changed these variables so we don't confuse this x with this value. So I didn't do it. So that will be 1.25. Plug for this x, this value. So that will be this x here, minus the 0, minus 1.25 over 5. Plug for this value, so this is, I'm writing with scribble to distinguish it, minus 0. So this is 1.25x minus 0.25. x5. That's the cumulative distribution function. Now, with this one, I can find this easily from here. I can find what is the probability of x equal or less than 0.8, which is this. So if I plug for x here 0.8, I get 1.25 minus 0.25, and this value will equal 0.91808. And to find the probability x equal or larger than 0.8, it's the same as 1 minus the probability of x equal or less than 0.8. So that is 1 minus 0.91808. So that is 0.08192. That's exactly the same as here. So if you are giving f of x, the equation, the cumulative distribution function, then you can find easily the probability of x less than any value. Just plug that value here in these equations, and you will find the probability. If you want it to be larger than, then it's 1 minus f of x. Okay, so we did this example. Now to find the median, not the mean, the median of a continuous random variable, we can solve it as follow. If we carry this integral and we put here the median x of m that we need to find, then this integration has to equal 0.5, because 50% of the data will be to the left of the median and 50% of the data will be to the right of the median. So I may give you the probability density function of a signal or of a random variable. They may look like this, or it maybe looks like this, and I want to find the median. So you have f of x or here, and to find the median, if you integrate here, that area has to equal that area, because half of the data to the left, half of the data to the right. Or in this one, the median will be half of the data here and half of the data here. So this integral has to hold. In general, not just the median, the percentile. Find me the value x of p such that 25% to the left and 75% to the right, or the 60th percentile. So we need to find this one. So if it's the 60th percentile, then this has to be 0.6. If I want the 25th percentile, then this will be 0.25. And then we solve this equation. And the median is the 50th percentile. So let's practice with this example. Find the mean and the median. So the mean is very simple. It's just x of f of x dx. So that will be from 0, the minimum value, to the maximum value. X, f of x is 1.25, 1 minus x to the power 4 dx. So that is 0 to 1, 1.25 x minus 1.25 x to the power 5. And when you integrate, so this will be 1.25 over 2, 1 minus 0, minus 1.25 over 6, 1 to the power of 6, minus 0 to the power of 6. And when you calculate this, you should get 0.625 minus 0.208, 0.41667. Okay, so that is the mean. It is somewhere here. Now the question is the median gonna be to the right or to the left? Can you predict, guys? Is the median gonna be larger than 0.41667, or is it gonna be smaller? From the curve, it seems the mean doesn't divide this area equally. This seems like this area is larger than this to me. So the median has to be less to divide this. So the median has to be somewhere here. So this area will equal this area. So we know that. Let's delete these. Okay, let's calculate now the median. So to find the median, then the probability from 0 to x of m of the density function should equal 0.5. Then we solve for x of m. So we're going to plug for f of x is 1.25, 1 minus x to the power of 4 dx. And when we integrate these, it will be 1.25x minus 1.25x to the power of 5 over 5, evaluated from 0 to x of m. And this should equal 0.5. So this will be, so then let's plug for x and x of m. So we get 1.25 x of m minus 0 minus 1.25 over 5 x of m to the power of 5, 0 to the power of 5 equal 0.5. And this is just 1.25 x of m minus 0.25 x of m to the power of 5 equal 0.5. Okay, now we have a problem. Now we need to solve for x of m. This is not a quadratic equation that we can do it by hand. This is to the power of 5. So we use a computer and write a code or a calculator, and you will find the solution for this equation. X of m equal 0.4022, the median. So as we predicted, it's not much difference from the mean, but we managed to predict. So the mean came 0.4166 here. The median came 0.4022. So that's here. This line, the blue line here. Now the last thing is Chebyshev inequality. Okay, the Chebyshev inequality, it helps us to find the probability. You don't know the probability density function of the random variable x. So let's assume we have a random variable x. We know the variance or the standard deviation, and we know mu of x, the mean. And we want to find the probability that the random variable x will be different than the mean mu x by a certain range. So the probability density function of this random variable x could be a Gaussian, could be exponential, could be gamma. We don't know. All we know is the standard deviation or the variance and the mean. And I want to know what is the probability that the random variable x will be larger or smaller than a range from mu x. So this is the range here. And that will be k sigma x. This is x minus sigma x will be larger positive, or it could be x here or x here. So I'm interested to know what is the probability that x will be larger than mu x by this much, or smaller than mu x by the same quantity. And Chebyshev will give us the maximum probability, overestimate. If I know the PDF, the probability density function, then I don't need Chebyshev. I can calculate the exact. But if I don't know, then Chebyshev tell us the probability will be 1 over k squared, where k could be any fraction, 1, 2, 3, 1.5 times the standard deviation. For example, and here we assume it's Gaussian, could be an exponential. So now here, if it's like exponential, I want to know what is the probability that x will be larger than the mean by this range, or in this range x. That means it's less than the mean by this range. That's why the absolute value. And that probability is 1 over k squared. So let's take this simple example. This could be a balanced weight gold. And I want to know what's the probability that that weight balance will measure the weight 3 gram above or below the mean, 75 gram. So how do we solve this problem? Well, we're going to use the Chebyshev. In this case, K sigma x equal 3. So K equal 3 over sigma x. So that is 3 over sigma is given for the random variable 1.5. So that is 2. The probability that the weight will be different than the mean by 3 gram equal 1 over k squared. So that is 1 over 2 squared. So that is 1 over 4. So that's 25% chance for this system. And we use the Chebyshev inequality if we don't know the density function, the pattern, the random variable x that we are measuring in nature or in electrical circuit or mechanical system. Then we use the Chebyshev to get this probability even though it's overestimated. Okay, this will end section 2.4, and next lecture we'll talk about linear function of random variable. Thank you.